Hey everybody, this is Mr. Sheeline. This is going to be the video lecture notes for Unit 4.1, Work and Energy. Before we get into the notes, just want to let you know that this is just going to cover the material in the notes. This is not going to be, or the check your understanding answers won't be in this video. That will be in a separate video, which I'll attach to the notes material later on. I just don't have it made yet, but in the future I will. So future Ian will have it. Future Mr. Sheenline will have it ready to go. So, okay, so just to let you know about that. So let's just get straight to it. Okay, so work. So work is a newer term, or at least newer. This should be like a newer idea of what work is. We've always talked about, just people in general have always talked about what work is, and obviously whether it's a career, whether it's something to do. But in the physics world, in terms of physics, work is the energy transferred to an object when a force is acting on an object, and it moves through a distance or moves just a particular distance. So we've been, you've read a little bit about it. You've read a little bit about energy. You did a little bit of calculation, or at least just looked at some calculations. Or I guess no, with the homework you have done some decent calculations with it, and hopefully you've got a beginning understanding of what work is. So remember, we've got energy. We use the energy in order to do work, and work is basically just whatever we use the energy for. Okay, and we represent the work with the formula force times whatever distance the object that we're affecting is moving. So here, the magnitude of the force is equal to F acting on the object, and it's parallel to D. So it's parallel. So if you have a force going vertically, but you have an object that is moving horizontally, which would be kind of weird, virtually your work would be zero, or at least seemingly so it would be zero if there's no force acting upon that, and it's just kind of floating. There is no work being done. And on top of that, you're applying a force in a different direction that's not affecting the motion of the sky. So, but if you were to have a force in the same direction as or at least on the same plane as the object is moving, then you can calculate the work. Okay, whereas in D is the displacement. So work done. So work is done when you lift an object, when you move an object, when you carry an object. It just has to be in one place to another. Now, it does get a little tricky at what that really looks like, and there's some pretty good examples of what that'll look like in the future here. Okay, and the check your understanding specifically. So work is done here with Legolas at the bottom, this little picture. Work is done to a bow when you bend it, and work is done to the arrow when it's fired. At the moment it's fired. Past the point it's been fired and it's moving, because you're not continually applying a force to it, there is no work being done. The work was done, and now it's got to just continue its motion. Okay? And then work is done to make a car accelerate. Now there you have an engine, you have a whole system that is continually adding a force and propelling this, in this case, a car forward. Okay. Now consider a situation though where you're pulling a bag on wheels at an angle of theta to the displacement, which you've already kind of worked on. This was number 4 in your homework yesterday. So you've already kind of dabbled in this. But if you notice, it's just basic trigonometry again. Look, here is the angle. Here is the force being applied. What kind of work is being done over the distance that and on the same plane as the distance traveled on this object. Okay, so here the force parallel or the force is parallel to the displacement. Okay, which then would say that the force that we're looking for is going to be the applied force multiplied by the cosine of theta, and that makes sense. Oh, come on, man. I lost my toolbar. Let's see if I can get it back. There it is. Okay. Don't lose my toolbar. Thank you. Jeez. Okay. And so let's get back. No. Okay. So that's let's see, where is it at? So the force parallel to the displacement is equal to F times the cosine. So the force applied times the cosine of theta. And we know this because this is the adjacent. If this is our theta here, this is the adjacent down here, and that is the opposite. And here we have the hypotenuse. So using SOHCAHTOA, okay, we know that we would have to use f times the cosine of theta in order to find a, and we know that just because cosine of theta is equal to adjacent over hypotenuse. Okay, in order to find a, we need to move the hypotenuse over. So we should understand that. And then part of number 4 as well that we kind of went over is the fact that when you have work done. When you have work done here, specifically at an angle, it does change the force needed in order to move something horizontally, or at least it can. If we have to talk about friction, and I'm just kind of relying back to number 4 on the homework the other day and how tricky it was in order to solve for the work done, because you weren't really given the force applied, but you were given the angle, you were given the coefficient, you were given the mass. So we'll continue to practice with that, and we'll continue to practice with really identifying all the different variables when it comes to calculating the work provided and work done on an object. Okay, and realistically speaking, that past slide was just to remind you, hey, trigonometry exists, and we use trigonometry in order to solve for work done. So let's take a look here. So here, let's try it out. So we've got here, work is going to be equal to F times D, which we know. And then here are all the variables that we need. So we want to find the work, but this work is being done at an angle of 30 degrees. The applied force is 10 newtons. Let's see, that should say 10 newtons, and then 30 degrees, and then 20 meters. Okay, so let's just think if it's that briefcase that we saw, that suitcase in the previous slide, we're going to be carrying that or sliding that briefcase over the span of 20 meters, and we're applying a 10 Newton force, or a force at a magnitude with the magnitude of 10 newtons at a 30 degree angle. And so let's just try this out. Okay, so I know, again, that this is my F right here. So our applied force here is going to be worth 10 newtons, and we can actually redraw this. Okay, so F is equal to 10 newtons. We need to find this guy here. I'm going to call it FAX, the applied force in the X direction. We have an angle here of 30, and then we're not going to worry about friction here. We're going to say that this is pretty much frictionless, because that would change things. Obviously, that would change things, because then we would have to find out what the net force is horizontally before we can calculate the work done here. Okay, so to find FAX, okay, because remember, we want to use the force parallel to displacement. Okay, so let's just do that. So let's see, where can I put it? So I'm going to put it over yonder. So I know that in order to find FAX, remembering from the previous slide, FAX is going to be equal to F times the cosine of theta, which that's going to be 10 times the cosine of 30, which is equal to 8.66. That'll be newtons. Okay, 8.66. And all we have to do now is just multiply 8.66 by 20. And why do I know that? Well, I know it's W is equal to F times D. And now we've got that force. That force is 8.66 in the horizontal times 20 meters. And that gives us 173 joules. So we're talking about energy now. Okay, and then let's just double check to make sure we got that. So Oh, what happened? Oh, that's not what I hit. All right, cool. And that all was lost. So remember, my answer was 173.2. Okay, so okay, that looks good. 173 Newton meters, or joules in this case. Wait a minute. Actually, no, sorry. No, it is just Newton meters. Sorry, not joules. Joules is energy. Newton meters is what we're talking about. My bad. Not joules. I was wrong before. It's Newton meters. Okay, but moving on. So units and directions. So remember, units here. Work is scalar. Work doesn't really care for the most part. Well, at least when we write it down, it's not to say that we don't take into account the direction, but think of it this way: by the time that we're calculating the work done, we've already taken into account the net force, like the net force that's acting on it, and because we've already and it's also the net force in whatever direction that we're moving, so it's already implied that you're moving in a particular direction, you're moving it. You're moving it, or at least you're affecting it in a way that's already implied that the direction has been accounted for, and we're past that when we're talking about the work done. So we really don't worry about it. So when we write our answer down, okay, it was right. God bless. I'm sorry, I'm confusing you guys. When we write this down, we write down that it's units, which is Newton meters, which is equal to a joule. And here's another way we can break that down. So 1 joule is going to be equal to 1 kilogram times meters squared per second squared. So remember, and the reason why it's this. So just to double show you why it's, because I'm sure you're looking at this and saying, why is that there? Because we know that 1 Newton is equal to 1 kilogram by meters per second squared. We know that, but now look it up here. So we're multiplying yet another meter, units of meters here, and that's why the meters per second. It's no longer meters per second squared. It's now meters squared per second squared for 1 joule. Okay. Okay. And then positive or negative work. So if the force and displacement are in the same direction, your work obviously is positive. But if the force and the direction are in opposition of one another, your work is negative. And I know that must seem weird after just getting done with the slide that says that it's a scalar, it's scalar units. And it's true, it's scalar units. It's still scalar. The thing you just have to be careful of, again, is that it's not so much about when we calculate the work done. It's more about taking into account the direction of the forces that we've already calculated in order to find the work. So just be careful as we go along. If make sure you draw free body diagrams. Make sure that you understand the context of the problem and you draw it out. You draw it out, you label all your variables correctly, you affiliate the different values with the particular variables correctly, you'll be fine and you'll be good. As long as you continue to keep track of which one's which. Okay. So again, work is scalar, but that doesn't mean that there isn't negative or positive work, because there can be positive or negative work in relationship to the distance it's traveling, and it does depend upon the force that's being applied. Okay. So here, work is positive, negative, or zero, depending on the angle between the forces and displacement. Okay. So think of it in this way. So because you're working with angles, obviously, especially like these angles, we're working with triangles, we're working with even circles, excuse me. So think of it in this way. So if all three of these examples are let's say on a circle, displacement is going to be equal to your radius, more or less. And if your displacement is equal to your radius, if your displacement is equal to your radius, in the idea that you're working in a circle, just think of it in this way: is exactly where is my work being done in relationship to the force applied. Okay. And so on the bottom you see here, so if you, and I know my little guy's in the way there, but it should say on your notes, but down here, of course, then that pops up. My goodness. Okay. But it does say down there, it says if theta is less than 90 degrees, your work is positive. If your theta is equal to 90 degrees, your work is 0. But then if your theta is greater than 90 degrees, your work is negative. Okay. So it's, again, and this is in relationship to the distance traveled. Okay. So your radius is equal to d. It's equal to your displacement. And if F, your force, is in opposition to the distance traveled, then this is what you would expect. Okay. So if velocity is constant, isn't acceleration 0? And if that's true, then wouldn't that mean that your force is equal to 0, and also your work is equal to 0? So whenever you talk about the work done, you must be very careful to specify which force does the work. So so think of it in this way: if the object is, as in, if the object is moving at a constant velocity. Well, as we saw, work can be done if we're moving at a constant velocity. Okay. Okay. And I'm just having, let's see. So here we're if we wanted to find out what the work of friction is doing on an object that is having an applied force in a particular direction, we can show here to say that F, the friction force times the distance, and we can find out what exactly the amount of work is being done, how many joules of energy, how many Newton meters is being expelled here. And in this case here we have the friction force is equal to 10. I know it's kind of hard to see, but it's right here. Okay, the friction force, because it says here, I believe that one says, that's hard to even read for me. Here it says friction force 100%. I'm guessing that this is the applied force. And it's we have the assumption here that this is the applied force is equal to the friction force. So if the friction force is the same, and if the applied force is 10 newtons, friction force is 10 newtons. So that's where this 10 comes from, times the cosine of 180. Okay, and then multiply by 1, idea being it's only moving 1 meter, and you'd have negative 10 joules. Okay, so again, it's how to phrase that. So again, it's looking for the amount of joules that's affecting this particular object. Okay, now let's say we wanted to find out what the applied friction is. Well, again, if the applied friction is going to be still just 10 newtons, in this case, cosine of 0 degrees times 10 times the 1, so 10 is the applied force cosine of 0 degrees, okay, and then times 1 gives you positive 10. So as you can see here, if we have constant velocity, the amount of work done both with the force and the friction are going to be they will be reciprocal. They will be the same in magnitude, but different in the fact that one will be positive, one will be negative. Okay, now what if we wanted to find the net force? Well, obviously the net force here, the net would be, well, your applied force is 10 joules, your friction force is 10 joules, negative 10 joules. 10 plus negative 10 is going to be 0. So the net work is 0, but there's still work being done. Okay. So if a question if a question did ask you, what kind of work is the applied force being done? Okay, if the question was specifically asking, well, how much work are you applying here, in order to maintain this constant velocity, your answer would be that the work done by the applied force, it would be 10 joules. But if it were to ask you what is the work done on the entire object, that's where the net work would come in, and you would have to figure out your net force, what's the distance, and you would then have to show that, oh, well, even though my applied force, I am producing 10 joules worth of work, overall my net work that's being applied to the whole object is zero, technically speaking, like we see here in this example. Okay. And then before we get moving into the check your understandings, you need to understand just a little bit about kinetic energy, because kinetic energy and work, for the most part, are intertwined with one another and do work with one another. So kinetic energy is the energy due to motion, which we should remember if you did take physical science way back when, talk about it in there. This was probably may have been talked about a little bit in one of Mrs. Volp's class. Maybe it's something that you don't remember and that you haven't practiced since middle school. But just remember, kinetic energy is the energy that comes from a moving object, or that's part of a moving object. And we represent that by kinetic energy equaling 1/2 times mass times velocity squared. And I'll lay it out here. So K is kinetic energy, M is mass in kilograms, V is velocity in meters per second, and the unit is joules. Okay. Unit is joules. So here, again, we can see here that kinetic energy measured in joules, work is measured in joules. They're pretty much the same thing. They just have two different equations here. And so you can go ahead and try these problems out on your own, just a quick try her out. So I'm not going to have the answers for these. But go ahead, try these out. These are pretty simple to complete, and you should see what's obvious about what happens if the speed is halved, what happens if the speed is doubled. Go ahead and try that for yourself. But I'll just quick read the problem. A 10 gram bullet has a speed of 1.2 kilometers per second. What is the kinetic energy of the bullet? So just make sure before you work on those, make sure you convert the 10 grams to kilograms, and then the speed from kilometers per second to meters per second. Okay, which that's pretty quick. Think about that. 1 kilometer per second. That's ridiculous. Okay, and then here are all the check your understandings. Now there's a lot of them. Okay, there's 3, 4. Now there's a lot of slides just because I want to give you space to complete these if you've printed these out. So here's A through C on this number 4 here. Number 5 has A and B. Number 6, of course. Numbers, and then here's number 7, and then number 8, and then the summary. I'll just quick talk about the summary real quick. But again, I'll have the videos. I'll have a separate video for the check your understandings. But here, 0 work done summary. So when work is 0, or when work is 0, when do we see work 0? Well, if our displacement is 0, then work is 0. If our force is 0, specifically like our net force, if our net force is 0, our work is 0. If our theta is 90 degrees, okay, if our work is 90 degrees, and the cosine, you can plot this in real quick, the cosine of 90 is 0, okay? And that's if the force is perpendicular to D, of course. Now, if it's moving in the upward direction, that's different. If it's moving in the upward direction, if it's moving in the upward direction, and your force is in the upward direction, you would have work. But this is the idea that if your displacement is perpendicular to your force, then here your force would be perpendicular. Its theta would be 90, and thus it would be work is 0. Okay. And then here's just all these different pictures of all the things that we've already seen throughout this good old PowerPoint. And then that's that. So that is the notes. If you guys still are having issues with some of the material in here, make sure you get a hold of me. What else? I can't think of anything else. Just make sure you go through the check your understandings. Go through the check your understandings on your own before you move on to the video that gives you the answers. I'll have that out shortly, so just stay tuned for that. Other than that, guys, if you don't have any questions for me, I'll see you in the next one.